Dear colleagues, let me introduce myself. My name is Voliansky and I represent Igor Sikorsky Kyiv Polytechnic Institute. The topic of my speech is numerical models of novel discrete-time chaotic systems. In today's world, chaotic systems are widely used in various scientific and engineering applications due to their unique ability to produce unpredictable signals. These systems are utilized to study and predict biological, meteorological, financial, and other processes and systems, and to design control systems for different technical systems, devices, and networks. At the same time, the primary application of chaotic system is in data encryption and secured data transmission. The increasing need for highly secured communication systems is driven by the necessity to transmit large amount of data for critical infrastructure cyber-physical systems, while restricting access to unauthorized persons. This interest in further fueled by the emergency of Industry 4.0 and Industry 5.0. Consequently, numerous chaotic systems have been developed and studied by many authors to provide desired system features. However, these systems are often considered as single-channel dynamical systems, which limits their ability to perform multi-channel data transmission. The use of control theory approach, which are based on the defining dynamical system motions by state-space equation, which are appended with observability equation, gives one the possibility to define as many system outputs as he desires. This approach also eliminates the need for subjective design of new chaotic systems, as it involves transforming of known systems. We demonstrate our methods by considering simple discrete-time chaotic systems, but we believe that it can be used to transform any chaotic systems. In our study, we solve the problem which you can see here in slide 2. These problems allows us to develop our approach as well as show its benefits. At first, in our study, we consider some generalized discrete map and transform it into discrete-time dynamical system by using approximation of differential operator. And you can see this approximation here, and also you can see the transformed finite difference equation here in this slide. This approach allows us to take into account many various state variables, and also it allows us to define some matrix motion equation for dynamical system of arbitrary point. Our further study is about appending the considered dynamical system with control input to extend its features. You can see this study here in slide 4. And as a result, it should be mentioned that we define some matrix operation which similar to transfer function for a linear control system. And this operator allows us to rewrite motion equation of any chaotic system in form which is shown here in slide 4. Also, it allows us to simplify the solution of this equation. Our next study is about considering some observability equation, which you can see here in this slide. This equation allows us to rewrite dynamical system motion equation in terms of only output variables, but not some state variable. And you can see here in this slide study, which is about algebraic observability equation as well as some differential observability equation. As a result, we obtain some difference equation which can be transformed into differential equation, and thus it allows us to obtain some novel dynamical system with predefined features and characteristics. Here you can see result of such transformation for well-known logistic map. This logistic map we transform into finite difference equation, and it can be rewritten in form of differential equation as well. You can see some block diagrams for novel designed system. Here in slide 7, discrete time system and continuous time system in left and right sides of this slide. As you can see, these block diagrams are similar, but it represents different nature of studied system. Here in slide 8, you can see simulation result for design system. This simulation results are similar to well-known simulation result of logistic map, thus it proves the correctness of our approach. Our further studies is about adding some additional state variables, and this addition allows us to design some chaotic system which is based on logistic map, but this chaotic system is a second order dynamical system. You can see its equation here in slide 9, and in slide 10 you can see the simulation results for this system. As we can see from this picture, novel designed system as well as system of first order produce the same outputs, but second order dynamical system also allows to produce some additional output, thus it can be considered as system with two outputs. Our next study is about considering the design system under some control signal. You can see this control signal here in slide 11, and here you can see the output of novel design system on this signal. Also, we study the design in such a way system with linear and nonlinear observability equation. You can see simulation results for this system here in slide 12. And conclusion in our work you can see here in this slide. Thank you for your attention.